All right, guys. So today we are going to start in and I'm going to introduce you to buffers. Buffers, you've probably had experience with. These are things that happen around you. They're even buffer systems that occur within your body, but you may not be familiar with what they actually are. So buffers are solutions that resist a change in pH when hydrogen or hydroxide is added. So they're going to resist a change in pH whenever an acid or a base is added to the solution. There are two most common types of buffers that we deal with. One is when we have a weak acid and its conjugate base salt, because the acid can react with any base that is added, and the conjugate base can react with any acid that is added. Then we also have a weak base and its conjugate acid, salt. And yet again, we have one substance that can react if an acid is added, and we have one substance that can react if a base is added. So here's kind of what we have. So here would be a buffer. We have the weak acid of acetic acid, the vinegar on the left, and then we have the sodium acetate on the right. So we have acetic acid as our acid. The acetate ion is its conjugate base ion. So that's its conjugate base salt. So we have these negative acetate ions that could react with hydrogen ions that are added from an acid. And then we also have the acetic acid that could react with hydroxide if it is added. Same kind of thing occurs if we have a base buffer. So here we have ammonia, and then we have ammonium chloride mixed together. So ammonia, remember, can absorb hydrogens, acting as a Bronsted-Lowry base. So it can react with hydrogens. We also have ammonium that can give up hydrogens to react with hydroxide if a base is added. So actually looking at these reactions that occur. So if we have a nitrous acid sodium nitrite buffer, so that means that we have nitrous acid, which is HNO2, and sodium nitrite is going to have that nitrite ion, which is the NO2 negative. What happens is if we add an acid, the acid gets consumed by the basic part of the buffer, which is the nitrite ion. So if we add some form of acid, so acid tends to have the H3O plus, the hydronium. If that is added to our base, our nitrite ion, what happens is the acid gives up its hydrogen to make water, and the base, the nitrite ion, accepts that hydrogen to make its parent acid, the nitrous acid. Now, what happens if we add a base to this is the base is going to get consumed by the acid. So remember, a base produces that hydroxide ion. If that reacts with our acid, our nitrous acid, our acid gives up a hydrogen to react with the hydroxide, which makes water, and leaves behind that nitrite ion. One thing that you will notice is in both cases, for a buffer, it will always produce water in some way, shape, or form whenever it is neutralizing whatever added acid or base we have. All right, so looking at what's happening more on the particulate level. Here we have a buffer solution. So notice that we have the parent acid and then the anion kind of floating around. If we add an acid, so we add hydrogen ions to it, the hydrogens react with those anions, producing more of the acid. But yet again, it's able to consume that acid. Whereas if the buffer solution, we then add hydroxide. Hydroxide is going to react with hydrogens. So it's going to take hydrogens from those acids and produce water, leaving behind more of the anion, more of the conjugate base. So here's yet again kind of what happens looking at the particulate level. So generally with a buffer, we have equal amounts of the acid and its conjugate base. Whenever we add an acid, this is the one on the left, we have more of the acid and less of the anion, the conjugate base. So pH would go down, but only a little bit, only slightly. Whereas looking at the kind of graph on the right, if we added the base, the hydroxide, that's going to produce more of the anions and less of the parent acid. So less of the acid means that the pH should go up, but yet again, only slightly. All right, let's look at another buffer. So if we have the ammonium chloride buffer solution, so ammonia is NH3, ammonium chloride is NH4Cl, but it's the NH4 plus is our conjugate acid for our ammonium. And yet again, if we add an acid, it has to get consumed by the base. So if we add acid, the H3O plus, add that to our base, the ammonia, the acid, the H3O plus, gives up a hydrogen, making water. And that hydrogen can't just float around by itself, so it will attach onto the ammonia to make that ammonium ion. And the flip side is true. If we add a base, that gets consumed by the acid. So adding a base, remember, is adding hydroxide. Our acid, our conjugate acid, is the ammonium ion. Hydroxide will react with a hydrogen to make water, leaving behind that ammonia base. So those are our typical, more common acid-base problems that we see. Or excuse me, buffer problems that we see. So we said for something to be considered a buffer, it is any solution that contains something that can consume hydrogen ions. So something with basic properties that can consume hydrogen. And something that can consume hydroxide ions, so something that is acidic. It has to have both. If it only has one, it is not a buffer. So it has to have something that can absorb hydrogen and hydroxide to be considered a buffer. So we need to look at in what other ways could a buffer system exist, because like we said, those two are the most common, but that is not anything. So we said that for something to be a buffer, we can have our weak acid and its conjugate base. We can also have the weak base and its conjugate acid. Another thing that we can look at is we can also have an amphoteric ion. So remember, amphoteric means it can be an acid or a base. So it can act both ways. So it can either gain a hydrogen or lose a hydrogen. Some things that are amphoteric that we looked at, we've talked about water before, but some of our amphoteric ions would be something like the hydrogen carbonate ion, or dihydrogen phosphate ion. Those could easily lose or gain a hydrogen. The other one that we can use is if we have a salt without spectators. So that means that both ions are going to produce an acid or a base. So whenever we looked at our salts and we were trying to determine if they were acidic or basic, remember we had those ones that we were able to cancel out because they would produce like a strong acid or strong base. We want things that cannot cancel, that cannot produce those spectators. So an example here would be ammonium nitrite. Because if you look at our salts, whenever we did these earlier, ammonium can produce ammonia, whereas the nitrite can produce the nitrous acid. Both of those, excuse me, that should be a 2. Both of those are weak acids or bases, so that neither one will cancel. So this one solution in itself can act as a buffer. All right, so here are just other examples of the 4 types of buffers we said we come across. So we have the weak acid and its conjugate base salt. So like hydrofluoric acid and sodium fluoride. Our acids, the hydrofluoric acid, the fluoride ion can be our base ion, our conjugate base. So notice that this can react with the hydrogen and hydroxide overall. Same thing for the weak base and its conjugate acid salt. We did that same reaction earlier. The salt without spectator, here we use the ammonium fluoride because ammonium can become ammonia. The fluoride ion can become hydrofluoric acid, which is a weak acid. So both of those will react. And then we have the salt that has that amphoteric ion. So here we have sodium hydrogen carbonate, and hydrogen carbonate can either gain a hydrogen or lose a hydrogen. So that ion by itself can act as acidic or basic. And in our next video, we're actually going to start doing calculations with buffers and looking at if we add a certain amount of acid or a certain amount of base, how does that affect the pH overall?